Hey guys, today we're going to be jumping into 2.5, which is imaginary numbers. This is going to be kind of a small lesson, but it's just kind of a mini lesson. I don't know how extensively you have worked with them before, but we're just going to need it for our next lesson. But so for the thing slash warm up, I have, can you take the square root of a negative number? And some of you might be saying no. Some of you might be saying yes because you know what an imaginary number is. And some of you might be saying, I don't know, we've been told both. And I would say the third option is probably where you should be, right? Can you take the square root of a negative number? We have, but sometimes when we try and do that, we say there's no solution, right? And really what we're talking about is you can, but you have to ask yourself, are you allowing imaginary numbers in your solution, right? If you're working in the complex plane, which is where imaginary numbers are, then you do have a solution. But if you are strictly working with the real numbers, like you don't want to take an imaginary solution, then you don't have a solution. And that's really what it comes down to. It comes down to whether you are working or willing to work with imaginary numbers or not, whether it is actually considered a solution. But the short answer, you can take the square root of a negative number in a way. And so what is an imaginary number? So an imaginary number is a square root of a negative number. And we use this very basic, you guys are definitely going to want to write this down somewhere. I equals the square root of negative 1. And then if you square it, right, the square root kind of goes away and you're just left with negative 1. And then I cubed is negative I. Well, that's because I cubed is I squared times I. And we just said I squared was negative 1. So it's really negative 1 times I, or just negative I, right? So that's where that comes from. And then again, I to the fourth is positive 1, right? Because I to the fourth is going to be I to the third times I. We just said I to the third was negative I times I. Wasn't that negative I squared? And we said I squared was negative 1, so negative 1. Isn't that positive 1? Right? So you might want to write these down so that you know them. But really, if as long as you know this first one, you can think your way through the rest. But I think it might be good just to get comfortable with all of them. And then I have this down here. Why are we even working with imaginary numbers? Like, aren't they just made up? And I have this YouTube video that I will put for the remote kids to watch elsewhere. We won't watch it right here. But the short answer is imaginary numbers. The word imaginary is such an awful name for them because they are real numbers, not real numbers in the sense that they're on the number line you're used to working with, but they do exist, right? And they have functions in the real world. And you can actually solve problems with them. You just kind of don't have the perspective yet. And one good point that this video makes is that, at one point, like way, way, way back, right? People didn't really have a use for negative numbers, right? Like you guys have no problem with negative numbers, but like very old civilizations, they didn't need negative numbers. They just needed to count, right? 1, 2, 3, 4, 5. They had no need for fractions, but then someone introduced fractions, and that completed everything in between those 1, 2, 3, 4, 5s that everyone needed. And so then they were like, oh, yes, we need that. But there was still never really any use for negative numbers. So a lot of even old mathematicians refused to work with negative numbers because they thought they were useless. But now today we realize that negative numbers are useful, right? Like in terms of debt, right? If you owe someone something, negative numbers are incredibly useful, right? And that's just a very basic thing, right? But, back then, all you see, what if I have 2 apples and I take away 3? That doesn't really make sense, right? But owing someone something makes sense. And that's kind of how negative numbers came to be. And this is just kind of like another more advanced variation of that, right? It's hard to picture like the imaginary plane of numbers, but they are real and they are useful to modern day things. And just to give you an example, these are the jobs that most use imaginary numbers. Look at that. Electrical engineer, mathematician, physicist, statistician, software developer. All very high-paying jobs, all growing jobs. More people need to do them. It is hard to find people to do these jobs, right? If you pick one of these jobs, you will have a job and you will make a lot of money, right? And not that money is everything in the world, right? But I'm just saying, for those of you that think it's useless, these 5 jobs literally use imaginary numbers constantly, right? And some of them might have kind of computer programs that do it, but you need to understand what they're doing with imaginary numbers in order to get the job. And if you all notice them, they're all growing jobs, right? There's always going to be jobs available for these. So the next time you think, well, why imaginary numbers? Right? And even if you don't plan on doing any of these, imaginary numbers are still what allows your phone to work, right? Imaginary numbers are in more places than you might think, and you never know what you might like when you get to in the future. So, complex numbers is another more appropriate name for imaginary numbers. They literally mean the same thing, kind of. And so I like to call them complex numbers a lot more than imaginary numbers because I just think imaginary is a horrible name. So A plus BI is how they are written. And when you have this A, I'll write this plus, and then I'll do this BI. This A part, this A part is the real part, and this B part is the imaginary part. And so some examples of complex numbers are 3 plus 7i, right? Here A equals 3, B equals 7. Negative numbers are fine too, right? A here equals -5, B equals 2. Again, negative numbers are fine, right? -6 minus 13i is an example. But then A and B can also be 0. So -i is an example of a complex number. B is just -1. A is 0. And even real numbers, just 27 is considered a complex number, right? B is just 0 in this case, and A is 21. And we just need to get a little comfortable working with these. So simplify to A plus BI form by adding the complex numbers. This one isn't too bad. A lot of people, they see 2 parentheses, and we've seen that a lot. You might start to multiply them, but just keep in mind, we have subtraction here, not multiplication. So let's just take it easy. So we can kind of get rid of the parentheses there on 7 plus 2i, and then we're going to have minus -3, which is plus 3, minus -3i, which is plus 3i. And then 2i and 3i are like terms, just like if we had an x on the end. So we could do 7 plus 3, which is 10, and 2i plus 3i is going to be 5i, right? And that's in the form A plus BI, so we're good. Now down here, we need to do some simplifying, right? So we know the square root of 81. That's nice. Minus the square root of -2. Well, if we remember our other rule, our A times the square root of B equals, right? We can combine them, or we can go the other way and split them up. I'm going to split this up, right? This is the square root of -1 times the square root of 2 minus the square root of 144 is 12. We know that one. And then plus, again, we could split this up into the square root of -1 times the square root of 32. So there's kind of a lot going on, but nothing we haven't done. 9 minus I times the square root of 2 minus 12 plus I square root of 32. We can go a little further with this, right? 9 minus 12 is going to be -3. We do those two. minus I square root of 2. Let's look at this for a second. The square root of 32, we can simplify that, can't we? Isn't the square root of 32, isn't that the same thing as the square root of 16 times 2, right? That 16 can come out as a 4, 4 square root of 2. So what we really have is plus 4I square root of 2, right? That 4 came out. Oh, now we have like terms. I squared root of 2, I squared root of 2. So now we have negative 3, 4 I squared root of 2 minus I squared root of 2 is going to be plus 3, 3I square root of 2, right? If we think of I squared root of 2 as like a whole chunk, we have 4 of this thing minus 1 of this thing. We're going to have 3 of this thing left over, right? And that's how I always like to think about it. I'm going to rewrite this just so it looks nicer. I accidentally brought up the keyboard there. I squared root of 2. Go away. And this will be our answer, right? We have A plus BI. B in this case is really just the square root of 2. But it's totally fine to have that I mixed in there. I like to have the I to the left of the square root. Otherwise, it might look like you're trying to put it in at the end. So simplify to A plus BI form by multiplying the complex numbers. Same thing here. We can do these numbers first, multiply in any order. 4 times negative 6 is going to be negative 24. And then 20 times 6 is going to be negative 120. And just like before, we can split that up into negative 24 times, this will be the square root of negative 1 times the square root of positive 120. So we have negative 24i. Now let me see if I can split up 120 nicely. That's going to be 60, or we can even do this. 40 times 3, 10 times 4, 4 is 2 times 2, we have 5 times 2. So this tells me that 120 is going to be 2 squared, right? 2 times 2 times, we have another 2 times 3 times 5. And you need a friend to get out of jail. This one is 2 squared, so does a friend. So that 2 squared is going to come out as a multiplication of 4. And then we're left with 2 times 3 times 5, which is 2 times 3 is 6 times 5 is 30. Right. And so then 4 times 24, 96. So negative 96 I square roots of 30. And that'll be our last answer for that one. And again, it seems like a lot, but again, nothing you haven't done, just throwing an I in there, right? This one, we have negative 9, and then there's really a negative 1 there, so we can multiply those two to get positive 9. And then negative 63 times negative 49. Well, when we combine those in there, that's actually going to be negative times a negative, which is a positive, right? 3087. Is that a nice number? I doubt it. So let's just find out. Divide by. Or you know what might even be nicer is the square root of 387. To get that, I multiplied 63 and 49. Or you know what might even be nicer? Screw this. Go back. So we have 9 and then times square root of negative 63 times the square root of negative 49. And then let's take that piece by piece instead of working with a huge number like that. So Again, we can break this up to the negative 1 times 63 and the negative 1 times square root of 49. Well, now look, now we have 9i, right? That's I square root of 63 times I square root of 49 is times 7, right? 9 times 7 we can do is 63. We have I times I, which is I squared, and then we have the square root of 63. And then I squared is negative 1, remember? So negative 1 times positive 63 is going to be negative 63. Square root of 63. Let's think about 63. Can anything be taken out of that? 3 times 21 and 7 times 3. So 3 squared times 7. The 3 will come out. So negative 63 times 3 times square root of 7, what's left over. And then this is going to equal negative 189 square root of 7. So no imaginary part because our I squared turned into negative 1. Right? And last one here. Now we have a binomial. So now we kind of go in order. Negative 7 times negative 10 is going to be positive 70. Negative 7 times negative 9i is going to be positive 63i. 7i minus times minus 10 is going to be minus 70i. And then 7i times negative 9i is going to be negative 63i squared. Let's be careful here. We have 63i minus 70i is going to be minus 7i. And then I squared, remember, is negative 1. So we really have minus 63 times negative 1, which is 70 minus 7i minus a negative 63 when we multiply those two together is plus 63. So what we really have is 133 minus 7i. And that'll be our answer for that one. And that is going to wrap up the imaginary numbers. I know I went a little fast and those probably seem crazy, but it's all the distribution and stuff you know. You just have to add I and I squared into that and work again more with your square